5. We have done serial equivalent circuits, parallel equivalent circuits, and we come to do theoretical and practical equivalent circuits. This equivalence circuit concept will also be used in practice and theory relation. This is an accumulator, commercial battery that we use in cars. So this equivalent circuit to this practical independent source is this: a voltage source in serial with a resistor. So that resistor value represents the physical and chemical material within this equipment. So it is independent voltage source, of which voltage is 12 volts. So ideal independent source is here. When the ideal, so we can, inside of this box you don't see any of those. So this is the equivalent of this one, meaning is this, we are going to observe this is going to be in practice independent DC voltage source. That means the voltage that you're going to see here is going to be 12 volts, but in reality it could be a bit different from that 12 volts, since because of this resistor value, if the resistance value is as small as possible, then the voltage drop in here is going to be very small. Therefore our ideal independent voltage source voltage is going to be equal to the practical independent source voltage. So if R is equal to 0, so this becomes ideal. So that means the practical equipment will be the ideal equipment, but in practice it is not like that. The quality of our equipment all depends on that R value. So resistance of the battery depends on the physical and chemical structure. When a practical battery becomes directly equivalent to the independent ideal theoretical source, when it practical battery becomes the theoretical source, when R equal to 0. Rechargeable standard battery examples. So this you can consider this part of this circuit true for the rechargeable batteries and standard batteries. When it becomes flat, we say flat means in Turkish bitti, pil bitti dediğimiz hal. This means the R value increased. So that means your quality of your source has decreased. Therefore you've got to recharge it if it is a rechargeable battery. When you recharge it, you are reducing the R value by giving the additional energy to the system. So that is recharging business. So this is one of the explanation of the practical equipment and the ideal theoretical equivalent of it. So there are some other examples that we could give. For example, a meter which measures the current of an element. What is the equivalent of this equipment? So here is the a meter's equivalent circuit, which is the equipment itself. Equivalent of it is the equipment functional part of it in serial with an internal resistance. So when you put this in, this internal resistance is going to be added to the R1. R1 is the load, the element of which current will be measured by this ammeter. So ideal case, when the internal resistance of an ammeter is equal to 0, so you can measure this current. So that is the actual current. Actual current is Vs over R1. So in this circuit here, if you're going to measure the R1's current, that current theoretically is V source over R1. That's the theoretical actual current. When you are trying to measure this current by using a meter equipment, so it's going to be a meter plus an R internal. So the current passing through this circuit is going to be Vs over R1 plus Rin. That's the measured current. So measured current is not equal to the actual current. When it becomes more or less the same as measured current when the Rin is very small when you compare it with R1. Let's say R1 1 kilo ohm and this is just 1 ohm. So then you can say that measured and the actual current will be more or less the same. But if the R1 range is in the range of that Rin, then you're in trouble. So the measured and actual values going to be different from each other. At least we can say that as a result, real and measured currents not the same value due to internal resistance of the ammeter. So we said we're going to put a connection between the real and ideal elements. We introduced the equivalent concept. So ammeter's equivalent is this. So this is the concept using the equivalent when you replace this equipment with the ideal elements like that. So another equipment that we use in electrical engineering is voltmeter, and its equivalent is a voltmeter in parallel with a resistor that R2. Assume that you have this circuit and you are trying to find out what the voltage of R2 is. So first of all, theoretically, the voltage of R2 is equal, actual voltage says, R2 over R1 plus R2 Vs. Vs over R1 and R2 is the current passing through this loop, and when you multiply this current with R2, you're going to get the voltage of R2. So that is the actual voltage, theoretical voltage. If you put a voltmeter in order to measure the voltage of this R2 resistor, you're going to put this in. When you put this in, this equivalent has got the meter part of it in parallel with internal resistance here. So this internal resistance is going to come parallel to R2. So in this case, the voltage that we are going to measure is going to be equal to this one. So R2 in parallel Rin, so that is the total resistance resistor here, and add R1, so that is behind that. That is the total resistor, equivalent resistor of this circuit, the whole circuit. If you divide Vs to this value, you're going to find the current. When you multiply that current with R2, you're going to get the voltage here. This voltage is this. So measured voltage and the actual voltages are not the same. When they become the same, when the Rin, internal resistance of the voltmeter, is infinite. When it is infinite, this is going to be 0, and the actual and the measured values are going to be more or less the same. So the quality of your voltmeter depends on the internal resistance value. For the voltmeter, if this resistance value is as high as possible, let's say in ideal case infinite, so it becomes the ideal voltmeter. The result, real and measured voltages not be the same value due to internal resistance of the voltmeter. Why we explained all that? We just mentioned to you that practical voltmeter's equivalent circuit is this, which has got internal resistor in it. So let's see what we have done after here. So we mentioned about serial equivalent, parallel equivalent, and we use these equivalent concepts in order to explain theoretical and practical relations of circuits. And we gave 3 examples for devs. So we're going to finish the video here and continue next time with Thevenin Norton equivalent circuits.